So now we're going to see when a series converges absolutely. Now that's not with an emphasis. It just means that we're going to look at the absolute value of a series and see if that converges. And so if the absolute value of the series converges, we say the series converges absolutely. This is why I want to say the ratio and root test are really good tests to determine absolute convergence, even though they're not the only ones. And so that is why I lecture or I cover the ratio and root test before I get to absolute convergence. But let's continue. The confusing part is that if the series converges but the absolute value of the series diverges, then we say it converges conditionally. So I have two approaches here. I have words and I have a picture. Okay, so the first thing is you want to take the absolute value of the given series and use any necessary test to see it converges or diverges. Okay, so original series, take the absolute value. What happens? If the absolute value of the series converges, then you're done, it converges absolutely. Yay! However, if it doesn't, then what do you have to do? So if the absolute value diverges, then you go back to the original series and test again. Okay, so then you get that result. If the original series diverges, then it just diverges. Everything diverges. But if the original series converges, then we say it converges conditionally. So I'm kind of a picture person, so this picture helps me, but I also have it stated out in words. You just have to have some type of algorithm for this process. So we're going to determine the absolute convergence or conditional convergence or the divergence of the following series. And now we've gone over all our tests, all 10 of them. Let's see if you can list them. Pause it, see if you can list 10 tests. Okay, so now look at your list. What do we have? We have geometric, telescoping, Nth Term Test, the integral test, the P-series test, up to 5, direct comparison test, limit comparison test, that's 7, ratio test, root test, and the alternating series test. All of those. Oh, wow. So if I want the absolute convergence, I have to first of all take the absolute value of that. That means I'm going to take off any negative part. So now I'm going to be looking at this series. So I have 0.1 to the nth power over n. That is not any series I recognize. I just saw in the ratio test if I have some powers of n that might be useful. So I'm going to try the ratio test. So the limit as n approaches infinity. And remember the ratio test, everywhere I have an n, I'm going to replace that with n plus 1. And then I'm going to multiply by the reciprocal of the original, because that's the same as dividing. And then look at that limit. Okay, so you really need to know your exponent properties. Keep the base, subtract the exponents. So that's just going to leave that to the first power. So I have 0.1. And now I have to take the limit of n over n plus 1. What is that limit? That limit is 1. So I have 1 times 0.1, that's 0.1, which is less than 1. What does that mean? That the series not only converges, but it converges absolutely, and I use the ratio test. That's an easy one, because if it converges with the absolute value, you're done. Okay, look at number 2. So if I take again the absolute value, what am I left with? I'm left with just 1 over n. Oh yay, I know that series. That's a P series. P is 1, and that diverges. But I'm not done. Okay? So I know it doesn't converge absolutely, but now it might converge conditionally, or the whole thing might diverge. Okay, so if that diverges, you're going to go back to the original series with that -1. What kind of series is that? When you have -1, +1, -1. That's an alternating series. So I'm going to use the alternating series test. Two conditions. Condition 1, the limit of the stuff without the negatives has to equal to 0, which it does. The second condition is that it has to be decreasing. So the n+1 term, it has to be decreasing, so the n+1 term has to be smaller than the nth term. Is that true? Yes, it is. This denominator is bigger than that, so that means this fraction is smaller than this fraction. So that's true. So that means it converges conditionally by the alternating series test. Why conditionally? Because the absolute value diverged. That's the only reason. Let's look at these. Okay, so again, you have some alternating series, but we want to know if they converge conditionally. So if I take the absolute value, then this series turns into 3 plus n over 5 plus n. Not a series I know. Let's see, I don't have any powers of n, not geometric, I don't know. Let's try the nth term test. How about the limit as n approaches infinity of 3 plus n over 5 plus n? What's that limit? That limit's 1, which is not 0. So this diverges by the nth term test. Again, I'm not done. I just know the absolute value series doesn't diverge. So, again, what kind of series was this original one? Alternating series. Well, if it's an alternating series test, what's the first condition? You have to take the limit of the non-negative thing. And we just found out that that does not equal to 0, so it still diverges by the nth term test, so the whole series diverges. And we're done. So go back and look. The first example, it converged absolutely. The second one converged conditionally. And the third one diverged. Those are your three possibilities. So let's look at example number 4. So we know it's an alternating series because of that, but we want to see the absolute value. So if I take the absolute value of this, I really need to look at the absolute value of the sine of n over n squared. I need to leave that absolute value there because remember the sign can be negative as well, so I need to make sure that that is positive. I know nothing about that series. So that kind of looks like a compare type thing. So I'm going to compare it to 1 over n squared. I know that series is a p series. P is 2, it's greater than 1, so that converges. But I'm using a comparison, so I'm either going to use the limit comparison test or the direct comparison test. I think the direct comparison test is going to be fairly easy. Okay, so I take the one I compare it to and this one, and if this converges, then I have to show that the sine of n, the absolute value, divided by n squared is less than or equal to 1 over n squared. Well, the good news is those are the same, so I just need to look at the numerator. Well, as I stated earlier, the sine of n goes from -1 to +1, and if I talk about the absolute value of the sine of n is always going to be less than or equal to 1. So this is true. So we could say, therefore, it converges absolutely, because remember we took the absolute value, by the direct comparison test. So you're having to put together all of those different types of tests to solve these problems. Ooh, natural log. Those are always nasty. Beware. Okay, so again, if I take the absolute value, I have this series. Just 1 over the natural log of n plus 1. That is not a known series. What can I do? How about let's compare it to maybe just 1 over n? I know about that one. Where am I getting that? I don't know. I ignored the natural log, I ignored the plus 1, and just kind of went with that. And let's see if this works. P equals 1, so this diverges, P series. And so if I want to use the direct comparison test, I would take these two things, and because it diverges, I have to show that this is now bigger than that. Is that true? Well, let's see. If we cross multiply, I'd have n, is that bigger than the natural log of n plus 1? You could make an argument that that is true, and this is true, and you would have to write your reasons, because n grows faster than the natural log of n plus 1. But if you don't know that, you can't just state it. So what else could you do if you weren't comfortable with that? Well, if you can't use the direct comparison test, you could always try the limit comparison test. So we have the limit as n approaches infinity of, remember, what you're choosing to compare it to goes on the bottom, and what you're comparing it to goes on the top. And so, let's see, if I multiply by that reciprocal, I would have n over the natural log of n plus 1. Ooh, if the limit goes to infinity, I have infinity over infinity, so I could use L'Hopital's rule. So the derivative of the numerator is 1. The derivative of the denominator is 1 over n plus 1. That simplifies to this. And as n goes to infinity, we get infinity. So that means this diverges by the limit comparison test. Okay, what diverged by the limit comparison test? Did the original series diverge? No, the absolute value. So since that diverged, I have to go back to the original series. And what kind of series is the original series? It's an alternating series. So the two conditions. Condition 1, the limit as n approaches infinity of 1 over the natural log of n plus 1. That goes to 0. Check. The second condition is that you have to show it is decreasing. Is 1 over the natural log of n plus 2, because that would be the next term, is that less than or equal to 1 over the natural log of n plus 1? And yes, it is, but if you can't see it, cross multiply, being careful. And this is true. Okay, so the absolute value diverged by the limit comparison test, or you could have made a case for the direct comparison test. But the original series converged by the alternating series test, so we can say that the original series converges conditionally. That one was a little bit harder. Anytime really you see a natural log, it usually means you're going to do a little bit more work. You really need to know the algorithm for absolute and conditional convergence. And so again, start with the original series, take the absolute value. If it converges, yay, you're done. If not, go back to the original, which usually is an alternating series most of the time. If it converges, you're done, and it's conditional convergence. And if it also diverges, the whole thing diverges.